Bismillah ar-Rahman ar-Rahim, and welcome to lecture number 9 for basic engineering mechanics. In today's lecture we would be covering some more examples for coplanar systems for equilibrium of a particle, and then we would move on to equilibrium of a particle in 3D force systems. So let's get started. So here we will have another example for a system for equilibrium of a particle where all the forces are coplanar. So the problem statement states that there are two members AC and AB which support a 30-pound crate, and we want to determine the tensile force developed in each member. So we have this very simple system. We have a load which is equal to 30 pounds, and then we have these two members which are supporting this load, and we want to find the tensile force in both of these loads. Okay, so first of all we would like to draw the free body diagram as we discussed last time. So the first step is always to draw the free body diagram. So here we draw the free body diagram. So the important diagram, free body diagram, would be of this hook here, because all the three forces are acting on this hook. If we draw the free body diagram of these two or this block, they are not going to help us solve the problem. So we are only concerned about drawing the free body diagram of this hook. So let's see. We have three forces on this hook. So let me draw a circle, and one of the force is the weight, which is downward force, and which is equal to, so let me draw this weight with this pinkish shade, and it is equal to W, which is equal to 300 pounds. The other two forces, one force is acting in this direction and the other force is acting in this direction, and so the directions, we need some angles to be able to make our calculations. We know that this angle is 45 degrees, again because this is 4 feet and this is 4 feet. However, this angle, this we can determine using the triangle like before we use. So we know that this side is 3, this is 4, and this is 5, and so now I have to name my forces. So what's the good name for this force? Let's see. So this force is going to be force FB, and this force is going to be FA. Okay, so with this our free body diagram is complete. Now we want to write the equations for the equilibrium and then find the unknowns. Okay, so what are our equilibrium equations going to be? So the two equations for equilibrium, as we have done before, are, so number one, we have the equation, we have so we can write, first of all we need some axes. So let me draw these axes. So this is my x axis and this is my y axis. So now I would first of all write the equation in x direction. So we have sum of all the forces in x equals to 0. And what are the forces in x? First of all, we have the x component of the FB force, and then we have the x component of FA force. There is no x component of this weight W, because W is directed only in the y direction. So this equation becomes this. Then what is the x component of B? This is just equal to FB, which is the magnitude of FB. So these have to be vectors. Okay, so this magnitude of FB times cos of 45 degrees, and with a minus sign because this has a negative component, x component, so we have FA, and then we have to do cos, which is just 3/5, and this has to be equal to 0. So this is our equation in the x direction. For the y direction, so let me draw a line here, and so for the y direction we would have the y component of FB, which is just FB sine of 45 degrees, and then we have to add FA times 4/5, and then this weight as is going to be a negative component, W equals 0. So these are the two equations of equilibrium, and we can solve them simultaneously to find the value of FB and the value of FA. These are the two unknowns. I am not going to solve these equations for you because solving simultaneous equations is something that you should be very comfortable with, and you should be able to do these things on your own. I hope the process and the steps are clear enough. Okay, so we move on, and here I just represent the same solution as we did before, the solution for these two equations. Okay, so now we look at another example. Here we have two springs, and the spring constant of this spring KAC is 20 Newton per meters, and this spring has a spring constant of 30 Newtons per meter. We have a mass of 2 kilograms which is hanging from this end, and we want to determine the stretch in the spring. So we want to find how much these springs are stretched. To find the stretch in the springs, we would first need to find the force in the springs. Okay, so again, very similar to what we did before, we would first have to draw the free body diagram of this ring here, and then we would use that free body diagram to solve for the forces, and then we would use those forces to calculate the stretch in the spring. So let me draw the free body diagram. First of all, we need a ring, and then we want to draw all the forces on the ring. We have a force which is directed downwards, which is equal to the weight of the block, and then one force we have in this direction, and the other force we have in this direction. Okay, so we have these three forces acting on this ring at A. So this point is A. So this force, we already know the value of this force, which is going to be 20 Newton. We are taking the value of G to be 10 meters per second square. So mass is 2 kilograms and the gravitational acceleration is 10 meters per second square. So we get a downward force of 20 Newton, which is equal to the weight of this block. So next is this force, and because this point is B, so let me just call it FB, and this force we can call as FC. Okay, so now we have drawn all the three forces, and now we would like to draw some angles also. So we know that this is going to be 45 degrees, again because this is 3 and this is also 3, and because this is 3 and this is 4, again we can draw the similar triangle like we did before. So we have this triangle here and this triangle here, and the values again is, this is 4, this is 3, and this is 5. Okay, So this it completes our free body diagram. Next step, as we discussed earlier, we need to draw an axis. So these are our axes. So this is the x-axis and this is the y-axis. Okay. Next, I would write the equations for equilibrium. This is exactly like what we did before, so I am going to do it rather quickly. So we would say that FB times 4 over 5, that is the first term, minus FC cos of 45 is equal to 0, and this is the sum of all the forces in X. So the second equation is just going to be FB times 3 over 5, and then we have to add the C component, FC sine 45, and then we have to subtract the 20 Newton force, which is this force, and this is equal to 0, and this is the equation for sum of all the forces in Y. So again, here we have the two equations, simultaneous equations. We can solve these two equations simultaneously to get a value of FP. So now then we would know that the extension in string AB, so let's just call it XAB, this is just the extension in spring AB, and this extension in spring AB is just going to be equal to FB, which is the force in the spring, divided by KAB. And similarly we can find the same formula. So this is for this spring, and we can do the same procedure for this other spring. I hope these points are clear enough. So this is the solution as we discussed before. First of all, we write these two equations. Again, in the book, and they are using this value of G, which is 9.81, but in this course we are going to use a value of 10 meters per second squared. Okay, and here we get the extension to be 0.793 meters and this extension to be 4.67 meters. Okay, so let's move on. So the next problem, we have determined the forces in cables AC and AB needed to hold a 20 kilogram ball in equilibrium and take this force F to be equal to 300 newtons and D to be 1 meters. So distance D is 1 meters, this is 1.5 meters, and so the ball has a weight of has a mass of 20 kilogram, which means it has a weight of 200 newtons, and this force F is 300 newtons. We can again solve this using the same method that we did before. We would draw the free body diagram of this ring A, and this would have four forces. One force would be directed along this C. So let me just draw it on top of this. One force is going to be in this direction, the other force is going to be in this direction, third force is in this direction, and the fourth force is in this direction. And let me just draw the arrows on all of these forces. Okay, so first of all we have to draw the free body diagram, something like this, and then we have to label all of the forces, and then we have to solve for the two unknowns. Okay, so again this is the free body diagram, just as I told you, and this is the solution, so you can look it up. Here we have another problem. We have this chord BCA, and there is another chord which is CD, So the cords BCA and CD can each support a maximum load of 100 pounds. So this cord can support a load of 100 pounds and this cord can support the load of 100 pounds. We want to determine the maximum weight of the crate that can be hoisted at a constant velocity and at the angle of theta for equilibrium. Neglect the size of the smooth pulley at C. We want to neglect the size of this pulley. We want to find the maximum weight of the crate here that we can pick up when these cords can hold a maximum of 100 pound load. A few important points to make here is that it's already given that the size of the pulley is negligible, so we would assume this point to be just like a point particle, and secondly, these two are separate strings. So this is a separate cord which has a maximum load limit of 100 pounds, and this cord which goes over this pulley also has a maximum strength. Maximum load that it can support is again 100 pounds. So first thing we would like to do is to draw the free body diagram as discussed earlier. So we have these three forces on this point C. One is the force in this cord and the other force is this, the third force is along this cord. Okay, so let me draw this point. This is going to represent this point C, and we are going to draw all the three forces. The first force is upwards, and the second force is vertically downwards, which is the weight of the block, and the third force is along something like this. Okay, and now we would like to draw. So we have the angle. This angle is equal to theta, and let me draw the axis here as also. This one didn't work out. Let me draw it again. So we have, this is our x-axis, this is our y-axis, and this angle is theta. And the three, so these are the forces. Okay, because the maximum load on the cord is supposed to be 100 pounds, so we assume that this is equal to 100 pounds. Okay, to start off, we are going to check whether this cord can take the load of 100 pound or not. We are going to assume that right now the mass of the block, the weight of the block is less than 100 pounds, and we're just going to put this as equals to 100 pounds. If with the end of this calculation we get that the load is more than 100 pounds, then we would have to assume that this cord breaks before this other cord. Okay, so we know that this block has some weight, we call that weight W, and because the only force on this block is through this string, so there is going to be a force W in this string, and because this cord is the same cord going over the pulley on the other side, and we already discussed that the tension in a cord is constant, so this force is again going to be, so let me just rewrite those things to clarify. So this force is Fa, and it is the magnitude of this force is equal to W, which is the weight times I hat. Okay, and this other force, let's call this Fb, and we know that the magnitude of Fb is also going to be equal to W, but it is pointed along this direction rather than this other direction. And this angle, again we have to draw a triangle here to specify the angles. okay, and this is 12, this is 13, and this is 5. So we have this picture here, and the next thing again we want to do is to write the equations for equilibrium. So first of all, we write the equation for sum of all the forces in X equals to 0, which basically implies that there is an X component of this force 100. So 100 cos of theta is the X component of this. There is no X component of this force, and the third force, again this weight is going to be W, because the magnitude of this force is also W. So I'm just going to say W times 5 by 13. So here we have the two terms for the sum of all the forces in X equal to 0. The other condition is sum of all the forces in Y equals to 0, which basically equals to 100 sine of theta, and then we have two negative terms. One is this term W, and the other term is again W times 12 over 13. I want to reiterate that why the force in along this chord W, this chord is also equal to W. The magnitude is equal to W, because this is the same chord going over this pulley, and we discussed earlier that any tension on the chord is equally distributed throughout the chord. Okay, so again now we can solve these two equations for W, and that would be our maximum load, that this chord DC that we can put here while keeping the load in this chord equal to 100 pounds, less than or equal to 100 pounds. Again, if W turns out to be greater than 100 pounds, then we know that this chord would break before this chord. But in this case, because this is vertically downwards, and so we would expect that this force, this chord would break before this other chord. Okay, so now we look at the solution here. So again, these two equations as we wrote them earlier, and then we solve them, we get the W to be less than, the value of W is less than 100 pounds, which means that, and theta is 78.7. This angle is 78.7, and the maximum load we can put is 51 point something, 51.0 pounds. Okay, so now we move on to our next topic, where we look at the forces in 3 dimensions. So previously we were looking at coplanar systems. Now we have forces which are in all of these 3 directions. Okay, so the obvious extension is that previously we had two terms, we had an I hat term and a J hat term, and now we have another term which is in the K direction, which is in the Z direction, and sum of all the forces are still going to be equal to 0, which means that sum of all the forces in X have to be equal to 0, sum of all the forces in Y have to be equal to 0, and sum of all the forces in Z have to be equal to 0. So now we have these 3 conditions rather than the 2 conditions that we studied before. Okay, so moving on, our procedure of analysis is pretty similar. We choose an appropriate axis. First of all, we draw a free body diagram, then we choose an axis, then we label all the forces, and then we make sense of the force to be positive or negative as we did before, and then we solve for the equilibrium equations. The only thing here is that rather than having 2 simultaneous equations, we have 3 simultaneous equations, and we can solve for 3 unknowns in this case. Okay, so all the coplanar force systems can be considered as a special case of 3-dimensional force systems where the force in Z is equal to 0. Okay, so here we look at this example we have a 90-pound load which is suspended from the hook shown in the figure. If the load is supported by two cables and a spring having a stiffness of 500 pound per feet, determine the force in the cables and the stretch of the spring for equilibrium. So we have this system here, and we are told that this system is in equilibrium, and we want to find the stretch in the spring, and we want to find the force in the cable. So we want to find the force in this cable, and we want to find the force in this other cable, and then we want to find the stretch in the spring, which is just like finding the force in this third cable. Again, the problem has already drawn these three axes, so we do not have to work in too much to draw the free body diagram. So let me just draw the free body diagram on top of this drawing. So we would have one force which is in this direction, the other force is in this direction, the third force is in this direction, and the fourth force is in this direction. Okay, these are the four forces, and now we write the equation of equilibrium. First equation states that sum of all the forces in X have to be equal to 0. So how many forces do we have in X? This force has no component along, so I should name the forces to make sense. So let's just call this FC, let's call this FD. This we already know is 90 pounds, so we do not have to give it a name, and let's just call it FB. So we have named all the unknown forces. Okay, so FB has no component in the X direction, and neither does this 90 pound force. This does not have any component in the X direction. The only forces which have a component in X direction is FD and FC. So what is the X component of this force FD? FD lies in the XY plane. So we know from this drawing that the X component is just FD times sine of 30 degrees, because the FD component is this component, and which this angle is 30 degrees, so this is going to be sine of 30 degrees. Okay, and then the X component of FC is basically going to be in negative direction, because this is minus going in the negative X axis. So this is going to be FC, and then we have times 4/5 from the triangle. Okay, so this is the first equation. The second equation, sum of all the forces in Y equals to 0, basically amounts to saying that this force has a Y component, and this force has a Y component. This does not have any, this 90 pound force has no Y component, and this FC has no Y component. So we would start off by saying that this is FB, and the other force which is in Y component is in my negative direction, which is FD, and we have a cos of 30 degrees because of this angle. So the last equation is in the Z direction, equals 0, which basically implies that the only two forces which have a non-zero Z component is this force FC and this 90 pound force. So we say that it is FC times 3/5, and then we have a minus 90 pound force. So these are our three simultaneous equations, and we have only three unknowns. We have FD, we have FB, and we have FC. We can solve these three simultaneous equations to find these three unknowns, and two of them would directly give us the two forces in the cables, and the third one we would divide FB by the value of K, which is 500 pound per feet, to find the stretching in this spring AB. Okay, so I hope the process is pretty clear. Again, the steps are exactly the same that we used to do in coplanar systems. except that we have, rather than having two components of each force, we have to understand that each force has three perpendicular components. Okay, so here we look at the solution. This is the free body diagram, as we drew the free body diagram on top of this figure rather than drawing it separately. Okay, and these are the three equations as we discussed earlier, and then we solve them and find these three unknowns. Okay, here we have another example. We would look at this example during our regular class session. It's hardly any different from the previous example. Again, we have these four forces on this point A, and we would draw the free body diagram of this point A. We would write these forces, and we would write the three equations of equilibrium like so. So this is the free body diagram, and then we would write the we would solve for the three forces as we have done before. Okay, so I hope this is clear. I'll see you in the next lecture.